Okay, so again, this is in yesterday's packet. Okay, so if you want to go to the Inspire, we talked about how to put it in polar mode. Okay, and we can look at this whole little family of graphs. If you look right here, all of these deal with cosine. So do you remember that at all, what our cosine theta looks like?
It is a circle.
It is a circle.
It's with
The leaves are
radius of 1/2.
No, it's just it will be a straight up circle. Okay, so here we'll just look at it in case you don't remember. So we'll go. Oh crap!
Oh, that is small. It's just like this. Sorry, it goes from 0 to 1.
Oh, So you want to be in polar mode? Oh my God! Okay, so we'll go
What? What are we talking about?
trig, cosine, theta, and what do you see there? It's pretty tiny. It's a circle. What's it on? What side is it on?
The right?
The right. And what's its diameter? 1. So it's like that, right? Okay. Let's look at the next one. What's been put in front of it?
Or number.
And what number would that be?
2.
Yeah, so now we're going to look at 2 cosine theta. What do you think happens to it?
It gets big.
Diameter.
It gets bigger, and in fact, it has a diameter of 2.
Oh, yes.
So what do you think happens on 3 cosine theta?
Negative.
I'm not getting it.
Inverse.
I think it's meant to be 2.
Just 82. Is this
So what'd you see?
Diameter of
Right? Now we have a diameter of 3, right?
This circle is in line.
That is not a Mistrager circle. It's more like an oval. All right, so what do you remember about negative 3 cosine theta? It flips over. What's its diameter going to be? 3.
Alone.
Okay. Okay, so look at the next one, our sine theta. What do you think that is?
On the Y, yeah.
It's going to be on the y-axis. That makes sense since y is the sine, right? Y value and sine value go together. What's its diameter? Do I even need to graph it?
No, you don't need to do it.
I don't need to, right? What's its diameter? It's 1. This is supposed to have a 2 in front of it. The next one's supposed to have a 2 in front of it. What's it going to be? Diameter of 2 and on the y-axis, right? And the next one?
Diameter of 3.
Yep. Hey, that one was pretty good. What about this one?
That's a diameter on the other side. But it's on the
Yeah, so now since it's negative, it's going to flip down here, right? Okay, so what do we notice about these graphs? They are all what? Circles. Yes?
Are we kind of going back to that thing where we're draw like roses and cardioids?
Yes. Cosine is on the x-axis. Sine is y-axis.
Yeah.
And then what's the sine do?
Across the
Yeah, like if it's positive cosine, it will be on the, oh yeah, like positive, negative, sorry. Okay, so positive is on the right, negative is on the left. When we're dealing with sine of theta, the positive is up, and the negative is down. Those are very technical terms.
2 plus 2.
Okay, so what about the next ones?
It's gonna be a little bit different.
Okay, well, let's see.
Coach Sanders, how do you set this expired?
I'll show you right now. So I'm going to add a graph. If you go to menu from the graph screen, sorry, no, escape. No, go hit menu, and then you go to graph entry edit, right? And you hit that. Are you with me, Austin?
I was just asking.
Oh, okay. Oh, okay. And then you go to polar. Okay. I need for you to pay attention. I don't have time to redirect because I got to replay this for 6th block. I got to get it uploaded. I don't have time. Okay. So I need to look at 2 plus 2 cosine theta. What do we have? That's a cardioid. That's a cardioid, right? Kind of looks like a heart. All right, so let's talk about this cardioid. Where is it? Where's the majority of it? To the right. What is determining that? The cosine part of it, right? And what is its distance from the pole to the outer edge? 4. There's the pole. There's the outer edge. Okay? And then what is its distance on the y-axis? 2 and 2, right? It went, my picture's really ugly, sorry. So it went 4 on the cosine side, right? And then it was up 2 and down 2. Just keep going off. Okay, so let's look at the next one. Let's look at 1 plus 2 cosine theta.
1 is less than. The 1 is greater than.
Huh.
Flap.
So what happened now? I have a cardioid with an inner loop. It's called a cardioid with an inner loop. All right? From the pole to the furthest point on the x-axis, how many units? 3. Right, so we're here and we're here. And what's the loop size? 1. And then where does it go? How far up on the y? 1, right? Okay, so are you making a connection with these numbers here? Look at these numbers right here. The 2 plus the 2 made this distance,
1 plus 2.
right? The 1 plus 2 made this distance. This 2 made the distance I went on the y. This 1 is the distance that I went on the y. Since 1 is smaller than 2, it makes an inner loop.
Is the inner loop equivalent to what?
Yes, it is. Yep. Since this number is smaller, and I think we call that A. I think it was like A plus B cosine theta. If A is less than B, it makes an inner loop. Okay?
Like, so on here, it touches 1. It touches 1 because the first number is 1, right?
Correct,
But,
uh-huh.
It just goes above that.
And it goes above that 1 because of that as well. Okay, so let's look at the next one. Okay, so what's the difference in this one now?
Two's bigger.
The 2's bigger than that, right? I don't like all these equations here. How do I move those?
You have to click.
Control
You can just
click.
click them, delete them.
Control click,
I
control,
know I
Oh,
grabbed it.
just make undo. Now move it over.
and then just hit enter.
Yeah.
Yeah, like I just want all of that to come away.
That
Come-
like the little hand thingy.
Do I have to click enter or what?
I think it's control click and it'll grab it. Then you move it down.
It's not working.
Oh, you got it. Oh, let me see. Show you.
Okay,
If you don't want to look at it all, you can just delete them, like just by clicking delete.
click,
Yeah.
delete.
Yeah, we said the same thing.
Sorry, I didn't hear. Okay, so look at this one, the highlighted one. Okay, so how many units long is it? 1, 2. Yeah, I can't even see that. Is that a 3? Yeah, that's a 3.
Yeah.
Okay, so the distance from the pole to the outer edge is 3. Okay, and notice these were all from the pole as well, right? Okay, so the pole, and that's 2 plus 1, that's your 3. But this number is bigger than this one. This number is 1, so it goes out here 1 unit. Okay, do you guys remember what this is called?
Like a lot, it's like
Like
L
something,
something.
like a lot.
Maybe that word.
Limbiskit.
Limniscus?
No, it's a limosome.
Like you.
Oh, like a
Okay.
It's a leggy.
Is there a
Why does this keep going off?
Throw it, throw away.
Stay on. Jesus. Where's my graph? I hate this calculator. Yes, there is a limniscate.
Wait,
Wait, so the distance from like the left side of the goal, is it from the 2 minus the 1?
Say that again.
Like the left side, the flat side,
Uh-huh.
how far away is that from the pole?
1 should be 1
On this
unit.
one, but like, as like a general speaking, is it the left, like the? I think it's the coefficient on the smaller number. Yeah, is it like the small, like the left number minus the cosine number?
Oh, it's not. You know what that
Hang on just a second. Because I'm trying to get my graph back.
Biscuit.
Go to 4, current, like if you're at the home, go 4, the current, graph will pop up.
You know you want to put packing the peppermint patty.
What? I just want the screen back. 4, as in the number 4? Okay, got it. Okay.
4 as in the.
Yeah, so this was 1, this was 2. Okay, so let's do this one for 2 plus 2 sine theta. Zip it, Vinny.
I'm sorry, don't pay over. He gets wet. Google's how to.
Oh my God. I don't know where the rest of it went.
Did it just stop at the end?
Yeah, I don't know. Because I didn't, my window isn't big enough. Okay, so how many units away from the pole?
4.
4. Okay, these two are the same, so what shape is it?
It's a cardioid.
It's a cardioid. Where does it touch the x-axis?
Is it technically touching 0 here? Like the origin, is it
Okay, so cardioid, lemosome, inner loop, and this is a convex, I think it's called.
That makes sense.
Yeah, convex lemosome.
Isn't there like a little on the C?
Yeah, there's a thing, yeah, there is.
What else called?
Okay, so tell me about this one. What's it going to be?
Lemosome with the inner loop.
Lemosome with an inner loop, right? The loop is how many units?
One.
What's the third one?
Convex.
Convex lemosome. Okay, so there's that picture. So I'm 1 unit.
Lion column.
No.
3.
1,000 places. No.
I feel like
Yeah.
Okay, and then there's your convex lemosome for the last one. So again, we're 3 units from the pole this way, 2 here. So it just flattens out on this side.
It's a little potato.
Say again.
A little potato.
Well, it's ugly, but. Okay, so which graphs go through the pole? That's when, and these are in the form, by the way, R equals A plus B. This is sine theta, and this is R equals A plus B cosine theta. Okay, I don't know what you remember about that. But if A over B is less than or equal to 1, it goes through the pole. If A over B is greater than 1, it doesn't go through the pole. And we have an inner loop when it's A over B is less than 1. If A over B equals 1, what do we have? No?
we have
Cardioid. Okay, so the reason we're sort of going through this exercise is you need to be able to sketch basic graphs. I will tell you that AP has gone away from making you do these on your own, like typically you would have a calculator. You do need to be familiar with just the pretty basic ones, but they've gotten almost every time they give you a picture or they give you a calculator, okay, in order to graph these. So we've got our circles, we've got cardioids, lemosomes. Over here, we're just going to graph like one of these because I need to get you going on the area stuff. But if you'll take a look, first of all, notice on these 6 graphs right here, what kind of number is in front of theta?
Odd.
An odd number, right? These are all odd numbers. Okay, look in problem number 4. The number in front of your theta is always even, okay? So let's just take a look real quick here. Let's do 2 cosine 3 theta. And let me change this window a little bit. Okay, and so I thought I changed my window well enough, but I didn't. Okay, so I was able to really slow it down here this time. And so what do you have here? Do you remember what this is called? It's a rose, and how many petals does it have? It has 3.
Three petals.
Then you start right here to go
And I changed my steps so that it really slowed down so that you could see exactly, or you could see a little bit better what was happening. Okay. So how many petals is that one going to have? 5. How many is that one going to have? 7. Okay. Let me give you the format here for these. This is like R equals B cosine N theta. B gives you the length of the petal. I'm going to let y'all go back. You can sketch these. And an odd N is the number of petals that you see.
That's from 0 to 2.5.
There are really 2 N petals. Okay, I don't know if you guys remember that. They draw on top of themselves. Okay. So I'm gonna let you go back. Y'all can fill these in. Let's look at one more here. Let's go down here and look at 3 cosine 2 theta. So remember the first number gives you the what? The length, right? Okay, so how many petals do you see here? You see 4, right? Okay, if you go back up here, there are really 6. Okay, but you're only seeing 3 because the second time around they graph on top of themselves. Okay, so same thing. B here is the length of the petal, and an even N multiply. Let's see. Multiply N by 2, and that will be the number of petals you see. So they're really always 2 N petals. Okay, so you can go back. This just has some summary here, like, you know, what the graphs look like. We've been talking about that. We'll come back to it a little bit more next week. I know you guys have been talking about, I've heard you say, lemniscate. That is the one, lemniscate. It's this one right here.
It's not a.
Wait, can you say that? I mean, spell it.
Lemniscate.
Right there.
It's on there.
Oh, lemniscate.
Stop it. Lemniscate. I don't know. Okay, so here's a sine one, here's a cosine one. But again, we'll come back around to those. But I really, really, really need to talk to you about area before you go. So take the packet that you got today. And the first thing I want you to do is flip it over onto the back. You have a blank page back there. And we're going to talk about the how the area formula for a polar curve comes to be. Okay, how we arrive at it. You already told me yesterday that you figured it had something to do with an integral, and you are correct. Definitely has something to do with an integral. Whenever we're dealing with integrals, what are we doing?
Adding up an infinite amount
Of subintervals, right? We are adding together an infinite number of subintervals. So here's how the area of a polar region came to be. Okay, formula for area of a polar region is based on the area of a sector of a circle. So, if you'll recall, if you want an area of a sector, do you guys remember how you figured that out? Okay, yeah, you're just figuring out what percent of the circle it is, right? So I would say theta divided by, I'm working in radians here, so 2 pi, right? That's giving me the piece that's shaded, or the percentage of it. And then I need to take that percentage as part, or it's the percentage of the what? Of the whole thing, right? So of the
area, like the shaded area over the entire.
Right, so I need to multiply this ratio by pi r squared. Right, that would give you the area of the circle. So you're taking the ratio that is shaded and you're multiplying that by the area of the total. And that gives you 1/2 r squared theta, right? These cancel out. So your area of a sector that you learned at some point, I don't know if in geometry you learned that as a formula or if you set up the ratio every time. You guys would have to tell me. I don't. Okay. So let's think about the graph of some polar region. Sketch your favorite polar curve. Okay, so we're going to say that this theta is equal to alpha, and this angle theta is equal to beta. So what is it that you think that I can do to calculate the area of this polar region? The integral from alpha to beta. So in other words, you're going to sum together what? An infinite number of sectors, basically, right? Okay. So, so if we take the function r equals f of theta, on the interval alpha to beta, and partition it into n subintervals. This should be sounding a whole lot like what? Riemann sums. So that'd be beta minus alpha divided by n. I'm sorry, I should have left myself some more room. I'm going to move this down here. What's that equal to? What is beta minus alpha divided by n equal to? The change, yeah, the change in what? Yeah, the change in theta, right? So the area would be equal to, you guys just told me it's a limit, right? It's a Riemann sum. Bless you. The limit as n approaches infinity of the sum from k equals 1 to n of what? What am I summing together?
Beta minus alpha,
Right, and I'll just call that delta theta.
delta theta.
But what's the area, what am I calculating there each time? The 1/2 r squared times that change in theta, right? And then we know that that's going to evolve into an integral. Okay, and so here is area of a polar region.
Integral.
The integral from alpha to beta of 1/2 r squared d theta. So that's kind of cool if you think about it. We were able to do with a circle what we have done with all of these other shapes by inserting rectangles, right? We've been inserting rectangles forever and ever. But we can now take this same idea of inserting infinite number of areas of a sector into a polar region, summing them together and being able to calculate an area. Okay, you good with that idea? Seem to make sense? Yeah? Okay. So go back to the front now, and I got 3 examples of problems to do with you. Again, when I first started teaching this course, this was a totally non-calculator section. And I got to tell you, it sucked. Okay? I mean, you had to use a bunch of trig properties to solve these integrals by hand. So the good news is you will either be asked to set up the integral and that's it, or it will be a calculator problem where after you set up the integral, you'll be able to solve it using your calculator. Okay? But I do have to be able to set it up. So here's that formula again for you. And now I want to find the area bounded by the graph of r equals 2 plus 2 sine theta. Well, we just graphed that. Let's see if we can do it without our calculator for right now. It is a cardioid, and it is a cardioid where? Where's the majority of it? It's on the top, right? Because it's sine. So it would be 4 units. It'd be 2 on the x. And it would look something like that, right? So what do you think the hard part of finding area of a polar is? Knowing what your alpha and beta are. Knowing what alpha and beta are is exactly right. Okay? So what do you think they will be for every cardioid? 0 to 2 pi.
But
Right?
if it was an even or an odd number or rows thing, would we have to go from 0 to pi?
You know what? You're going to have to figure out where the graph comes back to the pole. And that's going to be, those are going to be your limits of integration. Okay?
Oh, so every time it comes back to the
Every
pole,
time it comes
we
back
have
to the pole, any 2 consecutive values will give you your limits of integration.
Okay.
Okay, so if you think about it, I mean, for this one, I say 2 plus 2 sine theta, I need to know where that equals 0, right? So 2 sine theta would equal -2. Sine theta is equal to -1. So where is sine -1? -1, it's at 3 pi halves, and then to get to -1 again, you'd have to go all the way around.
Negative
Well, no, you'd have to
Oh, so
get
again.
back there again,
so
right?
3.
It would be 7 pi halves, wouldn't it? 2 pi. Yeah. Okay, but here's the thing. For a cardioid, you don't even have to sweat this. For a anytime you have a cardioid, you can always go 0 to 2 pi. Okay? So to calculate the area of this, I would have the integral from 0 to 2 pi. You can put the 1/2 out front if you want, since it's a constant. And then it would be r squared, 2 plus 2 sine theta squared d theta. And I'm here to tell you that a few years back when we had to do all that by hand, that's not fun. You have to square the binomial, apply a trig property, and this is what it looks like. Okay? This is what the homework used to look like for this section before it was. Isn't it beautiful? It's beautiful. It's like a piece of work. Okay. All right, so let's look at this one. I want to find the area of one petal of 2 sine 3 theta. Well, you might need to look at the graph of that. And it just wants one petal, right? Okay, so to figure out the area of that first petal, right, I need to figure out the alpha and beta are going to be the first place it's at the pole and the next place it's at the pole. So I want to set 2 sine 3 theta equal to 0. So sine 3 theta equals 0. So 3 theta equals inverse sine of 0. Okay, I need 2 consecutive values always. So give me the first 2 values where sine is 0. 0 and pi, right?
So it's 0 and pi thirds.
Yes, so that means 0 and pi thirds would be your limits of integration. So the area is equal to 1/2 integral 0 to pi thirds 2 sine 3 theta Okay, let me get through this last one with you real quick. I know I'm pushing. If you want to look at what it looks like, 4 cosine 2 theta.
What about 8? It would be 0 pi 8.
Okay, so again, remember any 2 consecutive values are going to work, right? So if you look at this thing like here and here would be good, here to here would be okay, right? Because it's just asking you for one petal. So let's set 4 cosine 2 theta equal to 0. So that means cosine 2 theta equals 0. So cosine inverse, so where is cosine 0? Okay, and let's think about this graph. What do you think might benefit you to do here? Well, I mean, you can certainly go pi halves and 3 pi halves. You could also go negative pi halves and pi halves. Do you see how that gets you this one? Okay, if you do the other one, you're just getting that pedal. That's fine. Okay, so this is pi halves. 3 pi halves is what you said, right? So theta is pi fourths and 3 pi fourths. And then that would just be your 1/2. Yep. And then I'm going to talk to you about that one a little bit more when we come back, because I need for you to be able to recognize that in a different way on a multiple choice question on the AP test. Okay, so what I want you to do is finish looking at those graphs, okay, the other ones we didn't get to, and then I want you to calculate the area of these 7 questions in this packet, okay? We'll have a lot to talk about on Monday, and that's okay. But if you'll do those for homework, that would be great. Yeah, if you would plug it in your calculator and get an actual value.